After studying this module, you shall be able to analyze how various physical methods have affected the development of bioinorganic chemistry, know the advantages and limitations of the physical methods for the specific application for molecular structure determination and characterization of electronic structures. Learn about how physical techniques such as Mössbauer, electronic and vibrational spectroscopy have been used for investigation of biomolecules. Introduction. In various spectroscopic techniques, one of the features which is common is the irradiation of sample with the light of a given frequency range. The light can be either scattered or absorbed, giving rise to a change in intensity that forms the basis for the physical method. The frequency of light and its associated wavelength may be used to evaluate the time scale at which a chemical phenomena can be probed by a given spectroscopic methods. Mössbauer spectroscopy. In Mössbauer spectroscopy, gamma rays emitted from the nuclei of the source atom of an element in an excited nuclear state are absorbed by the atom of the same element in the sample, and this is especially valuable for the studies of 57 iron in bioinorganic chemistry. From the isomer shift, that is delta, in millimeter per second, analogous to the chemical shift in an NMR experiment, some information about the metal oxidation and the spin states as well as the types of ligands coordinated to iron can be obtained. The low natural abundance of iron 57 isotope is the disadvantage of iron 57 Mössbauer spectroscopy in bioinorganic chemistry, often imposing enrichment either by reconstitution of the metalloproteins from the apo form, or if the route is not feasible, by isolation from growth medium containing iron salts developed by iron 57. For clusters of iron in biology, Mössbauer spectroscopy can be used to examine magnetic coupling phenomena, and for the mixed valence species to provide an evaluation of the rate of internal electron transfer reactions. Iron 57 Mössbauer spectroscopy has been especially useful in sorting out the various kinds of iron sulfur and iron molybdenum sulfur clusters in nitrogenase and the iron formal oxidation states. Although iron 57 Mössbauer spectroscopy has dominated bioinorganic applications of the technique, other conceivable nuclei are potassium 40, nickel 61 and zinc 67. Electronic and vibrational spectroscopy. Transitions between various electronic states lead to the absorption of energy in the ultraviolet, the visible, and for many transition metal complexes, the near infrared regions of the electromagnetic spectrum. Transitions between vibrational states occur at lower energies entirely within the infrared regions. Both electronic and vibrational spectra can be of tremendous usefulness in evaluating the structural and electronic properties of metallo-biomolecules. Electronic spectra. There are three major sources of electronic spectra in metal complexes, namely internal ligand bands such as are found in porphyrins, transitions related purely with metal orbitals such as d-d transitions, and charge transfer bands between the metal and the ligand. These spectral properties have been used to allot metal oxidation states, follow reactions and classify chemical species in the newly discovered systems. When spectral metals are present, for example, the 2 heme and the 2 copper centers in cytochrome C oxidase, the assignment becomes to identify each spectroscopic bands individually with some particular metal centers. In addition to the more conventional UV visible absorption spectroscopy, there exist numerous related methods for measuring electronic transitions that give insight about the electronic structures of metals in biology. One that we have already encountered is near absorption edge XAS, in which X-ray photons excite a 1s electron. Now, this technique has been successful to assign the oxidation states in the dinuclear iron oxoproteins such as methane monooxygenase, where iron 2 iron 2, iron 2 iron 3 and iron 3 iron 3 redox levels have been explained. The XAS method measures the absorption of variable wavelength photons by a metal containing sample. Vibrational spectroscopy. The vibrational spectra of proteins are exceptionally complex. Metalloproteins, in which the metal center has related electronic transitions, offer a special advantage in producing resonance Raman spectra in which the ligand vibrations are markedly improved. With modern instrumentation, including the availability of tunable lasers that can excite over a wide range of visible and near ultraviolet wavelengths, resonance Raman spectral studies have provided important structural insights about the coordinated ligands in metalloproteins. Especially valuable are the molecules in which intense ligand to metal charge transfer electronic transitions occur, such as in metal thiolate, metal phenoxide and metal azide complexes. Resonance Raman spectroscopic investigations of those chromophores can be used to recognize cysteine, tyrosine or exogenous azide coordination respectively. If the vibrational frequency of a coordinating ligand falls in a spectral region having little or no overlap with the protein band, or where the band intensity is very strong, both infrared and resonance Raman methods can be employed. Examples include studies of carbon monoxide and dioxygen binding to oxygen, transport proteins such as hemoglobin and hemocyanin. Another technical advance that has simplified the use of vibrational spectroscopy to bioinorganic structure determination has been the development of online computers and Fourier transform methodologies. Solvent and protein matrix background signals can often be averaged out by difference spectroscopy, where the spectra of the metalloproteins in two forms are subtracted from one another. The two forms might be with and without added substrate or inhibitor molecules, or isotopically substituted ligand derivatives such as oxygen 16, oxygen 16, oxygen 18, oxygen 18 or H2O and D2O. As with EXAFS spectroscopy, care must be taken in the laser Raman studies that the chemical integrity of a biological sample can be sustained during and after irradiation, preferably by activity measurements if achievable. Circular dichroism and magnetic circular dichroism spectroscopy. Circular dichroism is related to the difference in the absorption of left and right circularly polarized light by an optically active samples. CD spectroscopy has several important applications in bioinorganic chemistry. First, CD can be useful for detecting or resolving electronic transitions that are more difficult to isolate by simple absorption spectroscopy. This situation occurs because the selection rules for CD and the absorption spectroscopy are different, and because CD bands can be either positive or negative, so that overlapping bands in an absorption spectrum may be clearly delineated in the CD spectrum if the signs are different. Second, CD is a very powerful tool for examining the secondary structure of biopolymers. Different types of polypeptide secondary structures have distinct types of CD spectra in the ultraviolet region corresponding to absorption by the peptide carbonyl groups. Thus, it is possible to estimate the amount of alpha helix, beta sheet and other structures from the CD spectrum of a protein. In addition, CD can also be used to follow folding, unfolding transitions in polypeptides. CD can also be used to examine the secondary structure of nucleic acids, clearly distinguishing, for example, B form and Z form of DNA. Whereas only molecules that are chiral have CD spectra, all molecules exhibit CD spectra in the presence of an applied magnetic field. The technique that measures this phenomena is called magnetic circular dichroism (MCD) spectroscopy, whereas detailed theoretical analysis of the spectra obtained in most real applications are complex. The MCD method provides a powerful fingerprint approach to identify bound ligands in certain well-defined cases. A useful application has been to use MCD to assign the presence of a thiolate ligand coordinated to the low spin ferric heme centers in cytochrome P450 and in chloroperoxidase. In addition to its value as a fingerprint method, MCD has also been used to characterize paramagnetic metal centers in metalloproteins. In this application, information about the magnetic spin states is obtained by monitoring the temperature and field dependence of an MCT spectrum at low temperatures. Such an approach has been extensively applied to iron, sulfur and heme proteins. Summary: Iron 57 Mössbauer spectroscopy has been specially valuable in sorting out the various kinds of iron sulfur and iron molybdenum sulfur clusters in nitrogenase and the iron formal oxidation states. CD, that is circular dichroism, is a very powerful tool for examining secondary structure of nucleic acids, biopolymers, B form and Z form of DNA. MCD, that is magnetic circular dichroism method, provides a powerful fingerprint approach to identify bound ligands in certain well defined cases.